Being a little more formal, we say that if p is not equal to np, then for any constant alpha, at least 1, there is no polynomial time factor alpha approximation for the traveling salesman problem. For the proof, we reduce from Hamiltonian cycle, where we're given a graph, not necessarily complete this time, and we want to know if there's a cycle that visits every vertex exactly once. Here then is how we set up the traveling salesman problem. We assign a cost of 1 to every edge in the original graph G, and we assign a cost of alpha times v plus 1 for every edge not in the original graph. Clearly then, if G has a Hamiltonian cycle, then the optimum for the traveling salesman problem has a cost of v, 1 unit of cost, for every edge that it follows. Then a factor alpha approximation for the traveling salesman problem will return a Hamiltonian cycle h, whose cost is at most alpha times this number of vertices. On the other hand, if the original graph has no Hamiltonian cycle, then the cost of the Hamiltonian cycle returned by our traveling salesman approximation has to be greater than the optimum, but that must include at least one of these edges not in the original graph. Note that this term comes from following edges in the original graph, this one from following edges not in the original graph. There has to be at least one of them. Simplifying gives the lower bound of 1 plus alpha times v. Therefore, to decide the Hamiltonian cycle problem, we just run the alpha approximation on the graph with these costs here. Then we compare the resulting cost to alpha times v. If it's larger, then there can't be a Hamiltonian cycle in the graph. Any Hamiltonian cycle would have cost v, and our approximation algorithm couldn't have returned such a large cost. On the other hand, if it's the same as alpha v or smaller, then we can't have used one of the edges not in the original, so there must be a Hamiltonian cycle. Thus, if there were a polynomial time constant factor approximation for the general traveling salesman problem, it would yield a polynomial algorithm for the Hamiltonian cycle, which is NP complete. Unless p is equal to NP, no such approximation algorithm can exist.